Tell me,
Ma'am,
please. Please tell me. What is
with
the doubt?
only one Al2O3 mole.
Yeah, right. Okay, let's just do this. Okay. So this is basically Hall-Héroult process. Okay. So when we deal with Al2O3, what exactly do we do in Al2O3 electrolysis? Just see. So first of all, you have to understand that Al2O3 is a very high melting point substance.
Hmm.
Okay. It's a very high melting point substance.
Hmm.
So because it's a very high melting point substance, what exactly does that mean? That let's say you put it in a beaker. Okay. And when you put it in the beaker, obviously the beaker is also made up of some material. What do
Yeah.
we do preferably? We take it of some refractory material. What is a refractory material? A refractory material is something like bricks, which when heated, they become harder and harder rather than melting. So
Hmm.
refractory material is something which can withstand high heat, which can withstand high heat. You understand the point? So anything which can withstand high amount of heat is basically what? Is basically a refractory material. Am I right?
Yeah. Okay.
Got the point?
Yes,
Now
ma'am.
understand. Now understand. So what exactly is happening here? So we had this refractory material, right? All right. And then which we can withstand high heat. Understood the point? So what is happening? But even then, Al2O3 will melt at somewhere around 300, 3000 degrees Celsius. Now that temperature is a very high temperature.
Hmm.
So I understand. I hope you're understanding that Al2O3, when it is a very high temperature, what does that mean? That we have 3000 degrees Celsius temperature, which is very high melting point substance, right?
Yeah.
So what do we do if we melt it? So the temperature here will become 3000, but we are trying to do this electrolysis in laboratory. So what happens is that this refractory material, no matter how high temperature it can withstand, it can handle, but then this material will also melt, and there are high chances that the electrodes will melt in that temperature. You understand? Because electrodes will also be either made up of graphite if you are taking the passive electrodes, or they would be made up of platinum. So these are metals, and these metals will thereby melt, and these metals will also thereby melt.
Okay.
Got the point? So what exactly is going to happen? Just tell me. So we had graphite, we had platinum. You understand the point?
Yes, ma'am.
So what exactly does that mean? Tell me. That we have to lower down the temperature. So if we simply melt Al2O3, melting Al2O3 would not be the problem, but the problem is you have to continuously maintain that temperature to keep Al2O3 in the molten state.
Hmm.
So what do we do in order to lower down its temperature? What do? We melt Al2O3, and to that we add CaF2, and we add Na3Alf6. Na3Alf6 is cryolite, and this is called as fluorspar. All right. So what does cryolite and what does fluorspar basically do? Just see. So when we have Al2O3 and when we have cryolite, this. So you understand that let's say we have this crystal, and let's say every circle represents one full Al2O3. So imagine if we have pure Al2O3, it is going to be a very tight crystal. It is going to be a very tight crystal. Am I right? But you understand, once I melt it and I add CF2, CF2 will be of a different size. And you understand Na3Alf6 will be of another size. So what exactly happens is that when we have this particular beaker, what does that mean? That we will have the beaker, right? We will have three substances being mixed and all of them having different sizes. And all of them having different sizes. Yes or no?
Yes, ma'am.
Got the point?
Yes. Yes, ma'am.
Got it? So when all of them are of different sizes, so you will have one material this, one of this size, one of this size. So if you expect them to combine back, so let's say if the temperature drops below 900, obviously the temperature goes down, so it tries to solidify. But because we have now mixed atoms and molecules of different sizes, even if they join, even if they join, they will never be of the same size. So the crystal that is going to be formed will be unstable crystal and will be a very different sized atoms that do not fix well. So it will be a very weak crystal. And hence that weak crystal melt, will basically melt at what temperature? Will basically melt at lower temperature. Am I right or not?
Yes.
So that is called fusion process. So what do we do? That we fuse it with some other material. Fusing it with another material, we make sure that all the temperatures, let's say CaF2 temperature will be definitely lesser than Al2O3 temperature. The melting point of CaF2 will be lesser. Na3AlF6 will be lesser. Yes or no?
Yes.
Any doubts in this? So
No,
what
ma'am.
does that mean?
Oh, ma'am.
How many so if you say this temperature is melting point is 3000 degrees Celsius, and if you say the here temperature is 2000 degrees Celsius, and here you say the temperature is 500 degrees Celsius, the average will come out to be, the average will be the better, like average of 3, that is going to be 3000 plus 2000 plus 5000. So definitely that will be somewhere between what, this is going to be 5500, so this will be somewhere around 2100 degrees Celsius, so the average will be the lower than 3000. Am I right?
Yeah.
So the substances we are mixing must have lower melting point and must have different sizes. So that even if the temperature goes down, what exactly is going to happen? The particles will basically, if they try to combine and solidify, they will not be able to make a very strong crystal. And then even at lower temperature, if we maintain the lower temperature, let's say 800 or 700, at that temperature, the substance will remain in the molten situation, and it will not be a very high, temperature. Are we understanding? And in that case, my refractory beaker will also be left, and my the electrodes will also be spared from burning out. Are we understanding the point?
Yes, ma'am.
Got it. So that is the purpose of why we add it. Now, in that process, what happens is, let's say we would have just Al2O3. So then Al2O3 will give me two particular things, Al plus 3 and O minus 2. Am I right? So from
Yeah.
Al2O3, I will get one cation and I will get one anion. Am I right or not?
Yeah.
Any doubts to anybody? To you? But what are we adding? We are also adding CaF2 to it. So you understand that it is going to give me Ca plus 2 and F minus 1. And we are also adding Na3AlF6. So when this breaks, it gives me Al plus 3 ion. It gives me Na plus ion. And it also gives me F minus ion. Am I right or not?
Yes.
Got the point?
Yeah.
So now you understand, for the namesake of electrolysis, I have three cations: aluminium, calcium, and sodium. And I have two anions. Got the point?
Yeah.
So now if I carry out the electrolysis of Na3AlF6, CaF2, and Al2O3, what do I get? So from add cation, we know the series SO4 minus 2,
Yeah.
NO3 minus 1. Okay. We are going to have F minus 1, OH minus 1. Then we are going to have chloride minus 1, bromide minus 1, and iodide minus 1. Am I right?
Yes.
So I hope you're understanding. We are going to have Na3AlF6 like that. You understand?
Yeah.
And then here at as cations, we are going to have what? This, like this kind of series. So one, so aluminium, make sure we also made sure that aluminium is the one, because we have to anyway extract aluminium. So sodium is one cation, and you understand that we have uh, aluminium, and then we have sodium and calcium. So sodium and calcium, they will be the top ones above aluminium. So out of the cations, who is going to gain electrons? It is going to be aluminium. Am I right?
Yes.
So what does that mean? What does that mean? That clearly means that, ma'am, out of all cations, Al plus 3 will be less reactive metal.
Mm.
Less reactive metal is generally smaller in size. Yes or
Mm.
no?
Yeah.
And when less reactive metal is smaller in size, what exactly does that mean? That because it is smaller in size, it is going to lose electrons. It is going to gain electrons quickly and it will not lose electrons. So now you tell me, in the beaker, out of This is going to be my electrode. This is going to be my another electrode. And this is going to be my this. And this is going to be positive. Am I right? So
Yeah.
here, what are we going to have? We are going to have this beaker. We are going to have Na plus. We are going to have Al plus 3. And we're going to have Ca plus 2. So this is going to go there. Am I right? So
Yes.
at cathode, the out of the three cations, so Al plus 3 from the molten situation will go and hit the rod. This rod is negative because the battery has given it electrons. So it is going to gain 3 electrons and it is going to form aluminium solid. Am I right?
Yeah.
And at anode, what is exactly going to happen? Just tell me that at anode, what do you think we have? We have O minus 2 and we have F minus 1. So
Hmm.
at anode, what do you think is going to happen? Just tell me. So we're going to have O minus 2
Yeah.
and we're going to have F minus 1. So out of fluoride and oxide, who is going to be more strongly electronegative? Fluoride. So fluoride holds its electrons tightly. And
Yeah.
because fluoride holds its electrons tightly, what exactly does that mean? It would mean that it is oxide which is going to lose electrons. So O minus 2 will reach and O minus 2 will form O neutral and it is going to lose 2 electrons to these graphite electrodes.
Hmm.
Are we
Yeah.
understanding?
Yes.
And in that process, O minus 2. And the setup is not like that, but I have explained you the process. Okay. Sometimes we also add barium fluoride to that. Why so? Because it maintains the density. I'll come to that point. So O minus 2 is there. And it gives me what? It gives me neutral O plus 2 electrons. Got the point?
Yes, ma'am.
And then I hope you're understanding there are 3 electrons here and there are 2 electrons here. So 3 times 2 is basically going to be 6. So what do? You multiply this with 2. So your first equation converts to what? Al3 plus 6 electrons gives me what? Gives me 2 aluminium. And this is going to be 3 and 3. And this is going to be 6 electrons. So I have made the electrons the same. Am I right?
Yeah.
Okay. So what is better way of saying? So how many molecules will be formed? So if I say I have 3 moles of O atoms, 3 moles of O atoms, that means O2 will require 2 oxygen atoms for one molecule. So can I say when they combine, they undergo and form 1.5 moles of O2 molecules? Am I right or not? Got the point or not? So this is the idea of cathode and this is the idea of anode. Any doubts in this?
Miss three oxygen will form. Okay. Yeah. I
It's
got
a
it.
molecule, no?
Yeah.
So 4 molecules will form 2 O2. So 4 by 2 O2 basically. So 3 O will form how many O2 molecules? 3 by
Yeah.
2 O2. Because
Yeah.
we are not talking about, this is not 3 atoms. These are 3 mole atoms.
Hmm.
Is it clear?
Yeah.
Any doubts in this? Just tell me.
No. Got
Got
it.
it? So that is the idea. That is the idea. So you understand that when we are talking about the cathode and when we are talking about the anode, this is the equation. So
Hmm.
fluoride remains in the beaker, sodium and calcium, they both remain in the beaker. Understood the point or not? Just tell me.
Yes.
So we are going to have Al plus 3 being got, like we get this in the molten state. And this O2 gas which is being formed around cathode, around anode. And anode is made up of graphite. So I hope you're understanding that anode is made up of graphite. So this graphite will basically do what? This graphite is going to combine with oxygen and it is going to form carbon dioxide. So O2 will burn graphite. O2 will burn graphite. Am I right or no?
Okay.
Right? So you have to understand that in the electrolysis of Al2O3, oxygen burns aluminium, and hence, for every 1 kg of aluminium being extracted, it is around 0.3 kgs of graphite getting burned off.
Hmm.
That is the analysis. That is an experimental analysis. But once you calculate it, it is not exactly like that. Are you understanding my point?
Yes.
So this is the idea of aluminium stuff. This is how the electrolysis takes place. Understood the point?
Yes, ma'am.
Now, let's solve some numericals, okay? All right now. Okay, now tell me. A very important uh, concept of primary cells. One second. Okay, now understand. Now there is a concept of called as primary cell, and so electrolysis is done. Okay, and we have a concept of secondary cell. Now, what is this? Primary cell is also a kind of galvanic cell,
Hmm.
and secondary cell is also a kind of galvanic cell. But the secondary cells are those galvanic cells which are rechargeable,
Yeah.
just like a phone battery.
Hmm.
But the regular cells that you employ or deploy in the mobile, the watches, wrist watches, or the wall clock, right? They are primary cells because they are not rechargeable. Because they are not rechargeable. Do you understand my point?
Yes.
So because they are not rechargeable, what does that mean? Just tell me.
They
That
have to.
we have two types of cells. Got the point?
Yeah.
Now you have to learn their equations. Okay? You have to learn their equations. Now, what exactly do we get there? We get a regular primary battery. Okay. Now, the regular cell that we have is the dry cell. This kind of cell do you use in a regular life?
Yeah.
So you initially tell me that once you get this new cell, the wall clock starts functioning and the wall clock starts running. Okay, the needle of the wall clock starts running. But as and when after 6 months, this one cell will not function properly and it will stop giving me current or it will give me less current or less potential difference. And then exactly as a result, what happens? That, ma'am, the cell, the needle will stop working or the needles will move initially slowly. They will lose time and one
Yeah.
day eventually the clock will stop. Yes or no?
Yes, ma'am.
I hope you're understanding. So
Yes.
why is this exactly happening? So you understand that we have to understand how this cell kind of works. Okay. So what are these kind of cells? These are all galvanic cells. Galvanic cell was a very huge cell which was made in laboratory in two big beakers. So you could not carry that galvanic cell wherever you could go. But then scientists were successful in building such small cells which you can carry in your pockets. And you must have seen those batteries like that, you know, with two connections. Got the point?
Yes.
And when you see those batteries like that, it basically would mean what? It basically would mean what? Just tell me. That
They are.
we have this, these are such small things that we can carry and we can get a 30-volt potential or 60 volts potential and very, very portable. But they have in that small, packet or small packaging, they have all the cathode, they have all the anode, they have all the electrolyte in which the cathode and anode are dipped. And how do they function? Do you understand my point? What are we doing right now?
Yeah.
So the first cell that we basically do is a dry cell. Okay. Now, how does this dry cell works? We can use it in clocks, vagera. Now draw the structure. So what exactly is the structure? This is how the cell looks like. This is how the cell looks like. Okay. So this is the flat portion of the cell, and the cell that you generally get to see if ever ready is written on this, Nippon is written on that, or some any company's name. So that is a label which is being, which is being stick on
Marketed.
the boundary. But if you are capable of removing that sticker, then this basically becomes a zinc container. So you must have seen there is no label here. So this part is clearly visible. It's a shiny, silvery, shiny surface. This is actually a zinc container. Am I right?
Yeah.
Inside the zinc container, we have this dot, this kind of thing. This is actually nothing. This is a cap here. If you're capable of removing this cap, inside that we have a graphite rod. If you have ever tried opening this kind of cell, it's
Uh,
amazing experience to open this cell.
Actually, a lot of the batteries of some of my electronics leaked. So,
Yeah,
so that was the electrolyte, right?
yeah.
Mm.
And then you understand. So between these, we have a very porous paper. That porous paper allows all the electrolytes and ions to pass through,
Mm.
but it also prevents a direct connect with the electrolyte. You understand?
Yeah.
So here we have a paste of ZnCl2 and NH4Cl. That is going to be my electrolyte. You understand? So zinc is more reactive. It's positive because it is a donor of electrons. And this is a negative terminal. So this is gaining electrons. I hope you're understanding.
Mm.
This is a cell which is eventually by itself going to give electrons to me. Right? So imagine, let's say this is my remote. So this is the power button. This is the digits button, some volume button. And this is the end compartment where you insert the cell. Some devices they would require you to insert two cells. Am I right or not?
Yeah.
So inside it, how the circuitry basically works. The circuitry would basically work like this. So from here, it is going to go to all the buttons. Am I right?
Yes.
So what does that mean? So when we have this kind of situation, so you understand that this is a zinc container. This is giving electrons. After
Mm.
going through all the buttons, giving energy to all the buttons, it returns back to anode.
Mm.
Do you understand?
Yeah.
So if you imagine it here in this diagram, if you imagine it here in this diagram, here, okay? So how do you really relate with this? So the electrons are going to come out here and enter inside the graphite electrode. Once they enter the graphite electrode, you know that graphite cannot hold extra electrons. It passes these electrons through the membrane, through the paper membrane, to the electrolyte. Okay. Any doubts in this? Just tell me that.
No, sir.
Any doubts in this?
But ma'am, I get it, but what's the use of the second cell then?
Second cell? The second cell is also doing the same thing. Two cells at the same time would pass more current.
Hmm.
So it is going to have its own wire
Acha. Hmm. Yeah.
like that. It's a parallel connection of cells. But what I'm trying to tell you is that what is exactly happening? That every cell is like this one cell, and this portion that we see here is zinc portion that is more reactive. It loses electrons. So the one in the galvanic cell, we did this indirect redox reaction, yes or no?
Yeah.
So in this indirect redox reaction, what exactly happens? That we are going to have this rod here. We're going to have this rod here. It was copper sulfate here, and it was zinc sulfate here. Am I right or not?
Yes.
So once you connect it with the battery, what do you think is going to happen? This is negative and this is positive.
Yeah.
Got the point? So
Yes.
what is happening? This is going to be positive and this is going to be negative.
Yeah.
So I hope you're understanding it. This was not the battery. We had a bulb here. That because the cell we have made two beakers such that one is a highly reactive metal and one is a less reactive metal. So one was losing electrons. So the one which loses electrons is basically becoming my oxidation area, and wherever the oxidation takes place is what? Is anode.
Yeah.
And wherever is the reduction is called as
Cathode.
cathode. So you get this area, and this is anode. Am I right or not?
Yeah.
So what exactly does that mean here? That anode loses electron and
Hmm.
cathode gains electron, and then we had the salt bridge. Do you remember that process?
Yes.
So here that is exactly the same thing. So my first equation at anode, what am I going to write down? My first equation at anode here is going to be what? And understand that this was actually yeah. And here we had MnO2 in some space here. We had MnO2 being filled. So it was like that. MnO2 just after the paper, and then the outside area it was ZnCl2 and NH4Cl. And then it was zinc compartment.
Okay.
Okay, so this was the composition. This is actually the composition we do not know, but this is actually there in kind of cells we use in our daily basis level. So at anode, who is going to lose electron? The more reactive element, which is zinc. So zinc converts into Zn plus 2 and loses 2 electrons. So from here, these 2 electrons go, and now this area will have Zn plus 2. Are we understanding this part? Understood?
Yes, ma'am.
Got the point?
Ma'am, here the anode is not positive.
Anode is positive.
So, ma'am, if the anode is positive, won't.
Sorry, anode is negative. I'm so sorry.
Okay.
And this is positive. Because more reactive is the donor of electron. It is a galvanic cell. I'm so sorry. Yes. Anode is negative because this is a it is not an electrolytic cell. It is
Hmm.
the electrochemical cell,
Hmm.
galvanic cell.
Okay.
Now is it clear?
Yeah.
Okay. Now these electrons reach here. They do not stay inside the graphite rod. They pass through. Okay.
Yeah.
Now how do they react here? ZnCl2, you don't have to worry about ZnCl2. Okay.
Hmm.
But we have NH4Cl outside. So you have to understand that NH4Cl is obviously broken down into two cations and anions, NH4 and Cl negative. Okay. And
Yeah.
NH4 plus is basically present how? Why am I telling you this? You should know the reactions. NH4 is also broken down into ammonia plus H plus.
Yeah.
Okay. Now, understand ammonia is a gas. When ammonia is a gas, so you understand that if we allow ammonia to build up inside the cell, there is a risk of cell bursting out at any point in time.
Yeah.
But do we see the real bursting of these cells? We do see the bursting of the batteries where the mechanism or system is not made properly. But if we do not see the mechanism like that, I hope you're understanding when we have ammonia, you understand. So that ammonia will basically do what? So that ammonia, we do not allow it to get accumulated there. So I hope you're understanding that when ZnCl2 we have Zn plus 2 and Cl negative. So whatever ammonia is being formed, whatever Zn plus 2 ions we have here, or whatever ammonia is being formed, or whatever Zn plus 2 ions are being formed by ZnCl2, they both form a complex with ammonia and they convert that gaseous ammonia to the solid state. I hope you're understanding. Got it?
Oh,
So gradually and eventually ZnCl2 and these Zn plus 2 ions in the our node. So this Zn plus 2 is also getting consumed.
yeah.
This Zn plus 2 is also getting consumed to hold what? To convert this gaseous ammonia into a solid product. And that solid can be placed, can remain anywhere inside the cell without, you know, uh, the cell will not thereby increase in size. You must have seen the cell which gets little bit blown up because of the gas. Got it?
Hmm.
So some gas fills in it and it becomes little fatty in size or becomes bigger in size. Why? Because the gas forces it to, blow up like a balloon. Do you understand? So that is not happening. You must have seen certain old phone batteries which get swollen up because of the gas being filled in them.
Hmm.
Because that gas is not converted into some solid substance. Are we understanding my point?
Yes, ma'am.
Okay. So when we have ZnNH3 whole solid this, so you have to understand what is the role of ZnCl2. It provides Zn plus 2. Anywhere Zn plus 2 in the anode, Zn plus 2 from ZnCl2 or from anode
Yeah.
will convert the gaseous ammonia to solid complex. तो Zn+2 अगर कंबाइन करेगा अमोनिया के साथ तो कितने से कंबाइन करेगा देखो. So what is Zn's charge here? Zn's charge is +2. Double the charge, 4.
Yeah.
This doubling of the charge will basically do what? That many ammonia will combine with it. So what is going to be the complex? We're going to have Zn, NH3. The charge of Zn is 2, so 4. And the charge remains the same. So this is going to be what? This is going to be Zn, NH3 whole 4. Are we understanding the part? So we're going to
Yeah.
have Zn, NH3 whole 4.
Okay.
Got the point? So this is the solid complex which is being formed. The first part is clear. What are these electrons doing? What is the use of Zn+2? Then what is happening at the anode, at the cathode? Okay. So at cathode, what do we get to see? We get to see MnO2 and we get to see NH4 plus. Got it?
Yeah.
And NH4 plus and Cl negative. And then what happens? Now understand. So you understood that NH4 plus breaks into NH3
Yeah.
and it gives me H plus. Ammonia is being gaseous. We cannot allow it to built up inside the battery. Otherwise, the battery will burst out. So we convert this into a solid substance. But if you understand, if we have H plus and Cl negative, they form a strong acid called HCl. So if we do nothing about H plus, you understand that this H plus will start reacting with the jacket of the cell, which is made up of zinc.
Hmm.
Understand my point?
Yeah.
And when it starts reacting with the jacket of the cell, what exactly do you think is going to happen? That eventually the cell will. So I did this one experiment. What did I do? I bought a new cell and I left it in sun for over a month. And what I found was that the cell started leaking. And my cell, I pulled off the label of the cell. And then what I found was that the cell was leaking. And the silvery, shiny metal, it was no longer silvery, it became little corroded. Because HCl started coming out of the cell and it started reacting with the zinc jacket. So that cell was not a fit or better choice to be put into some appliance because then that cell was leaking. So it would again, corrode the material of the device that I'm going to use it in. You understand the point? So we have to do something about this H plus also. We cannot allow this H plus to be moving freely because ultimately then it will combine with Cl negative coming from NH4Cl and ZnCl2. Because the Zn plus 2 and Cl negative. This Zn+2 is being utilized to convert the gaseous ammonia to solid substance. So we are left with lot of Cl negative in the beaker and that Cl negative will then eventually combine with H plus to form HCl. If
Yeah.
that HCl builds up, it will destroy the zinc jacket. We cannot allow the zinc jacket to be destroyed. Are we
Yeah.
understanding my point?
Yes.
Got it? So then what happens? Then what happens? Just tell me. Got it?
Yes.
So you understand what happens at cathode. Now cathode gains the two electrons. So cathode gains the two electrons given by the zinc anode and they reach the graphite rod and they enter and these electrons are also there. These electrons are also there.
Hmm.
Got it? So what happens? So we're going to have MnO2 plus NH4 plus
Hmm.
plus negative plus two electrons.
Yes.
Now see what is happening. So MnO2 is basically made up of Mn plus 4 and 2O minus 2.
Hmm.
NH4 is basically NH4 plus and NH3 and H plus. So one O minus 2 combined with H plus and they form OH negative. Are we understanding?
Yeah.
Okay. These two electrons are taken up by Mn plus 4. So Mn plus 4 converts to what? Mn plus 2. Are you understanding? Are you understanding?
Miss Emin. Okay. Yeah. Hmm. Got it.
So two electrons. So understand how it is exactly working. So ammonium is giving you a lot of this, right? So every ammonia will give you a lot of H plus. So we take two MnO2. So two MnO2 will have one MnO2 molecule
Hmm.
and one MnO2 molecule. How will this one MnO2 molecule break? It is going to give me Mn plus 4, O minus 2 and O minus 2. And then another MnO2 will give me Mn plus 4 and O minus 2 and O minus 2. Am I right or not? So in that process, two electrons, how does it divide? Not one Mn plus 4 gains, it converts into Mn plus 3. So one electron by one MnO2, another electron by another MnO2. So I hope you're understanding the situation. We have two MnO2.
Oh.
Got the point?
Mhm.
You understand?
Yeah.
So basically, one MnO2 molecule is basically doing what? It was NH4 plus, it was Cl negative. We had two electrons, but at with one MnO2, I'm using only one electron at cathode.
Okay.
So how does this process proceed? So we have Mn plus 4, O minus 2, O minus 2. This NH4 plus will break down into NH3 and H plus. If this H plus remains, it will combine with Cl negative. We cannot let that happen because it is going to form a strong acid. So one H plus combines with what? One H plus combines with one O minus 2 and it forms OH minus 1. And the benefit of OH minus 1 is what? That it is now basic. And this basic will then start neutralizing any acid being formed. But anyway, and that one electron will be gained by Mn plus 4 and it will convert into Mn plus 3. So how will this Mn plus 3 convert? So NH4 plus will convert into ammonia, which will eventually be taken up by Zn plus 2 to form a solid. Then we will have what? Mn plus 3. Now Mn plus 3 will be neutralized by one oxide and one OH negative. So how do we write this down? We write it down as OOH plus ammonia. Got the point?
Yeah.
And the Cl negative remains like that. And Cl negative, if it remains like that, it is of no use to us. Why it is of no use to us? Tell me. Why it is of no use to us?
Miss.
Because it is not forming any acid. So it may remain, it is not gaseous also. You understand? And if whatever Zn plus 2 we have, Zn plus 2 will combine with this to form ZnCl2, which is a part of electrolyte. So this is kind of regenerating the electrolyte, which enhances the life of what? The
Okay.
cell. Got the
Cell.
point? That is why these cells can run for like 6 months because it is taking a lot of time for the electrolyte to get completely utilized. The day the electrolyte gets utilized completely, gradually and eventually you see NH4Cl is getting utilized. NH3 is being formed, and H plus is combining with O negative. So the moment NH4Cl gets utilized completely, the cell will stop. Are we understanding? So here, what is getting oxidized? You tell me. What is getting reduced? Mn plus 4 is getting reduced to Mn plus 3. I hope you're understanding. And who is getting oxidized? Zn is getting oxidized to Zn plus 2. That is at anode. And NH4 will do what? It will form NH3 and H plus.
Yeah.
Got the point or not?
Yes.
So that is the idea. Got it?
Yes.
Any doubts in this? So what is going to be my final equation at cathode and anode? Simply you have to write down that at anode, we have zinc converting itself to what? Zn plus 2 electrons. At cathode, obviously, only one electron is being utilized. So either you write equations for two MnO2 molecule, but if I'm trying to tell you that what is happening with one MnO2 molecule, so I hope you're understanding that we have NH4 coming from the electrolyte plus one electron from zinc. And Cl negative is there. So NH4 breaks down into NH3 plus H plus. So my final equation becomes MnOOH. I hope you're understanding how we have got OH. So Mn is
Yeah.
plus 3, O, 1 O minus 2 remains 1 O minus 2. And then we have OH negative. And then we get ammonia gas. And the Cl
Yeah.
negative is there. There is no H plus in the beaker. And because we have no H plus in the beaker, that is the basic idea. Are we understanding this part or not?
Yes, ma'am.
Any doubts in this?
No, ma'am.
Got the point?
Yes, ma'am.
So this is a primary cell. Why? Because its electrolytes cannot be regenerated. So once this cell gets utilized, you cannot regenerate its electrolyte, and hence once electrolyte is over, the cell will stop working and you cannot recharge it. Hence, it is a primary battery. Are we understanding my point or no?
Yes, ma'am.
Any doubts in this? Okay. Then what do we have? Then we have the mercury cell, which is also called as the button cell. Then we have a mercury cell, which we also call as the button cell. Okay. So what exactly do you know by the mercury cell, or what exactly do you know by the button cell? Just understand. So once we have the mercury cell and once we have the button cell, so you understand what is the anode. So it is a very small cell like that, like that. This you use where? This you use in hearing aids, or this you use in watches. You know, the small devices. This also you use sometimes in all the digital watches that we have these days, right?
Yeah.
This we also use in our thermometers, the digital thermometers that we get. That is also you use mercury cells. So what exactly do they have here? You understand. So they basically, there is an anode. So what is the anode? It is basically the zinc metal plus zinc amalgam. They both make one anode. So we have zinc as a solid metal, and zinc amalgam is going to be my paste of zinc in mercury. All right. And just like cathode here, just like in the above cell, the dry cell, the cathode is going to be graphite. But what do we call it here? We call it as a carbon cathode.
Mhm.
Okay. We call it as a carbon cathode. Are we understanding my point?
Yes.
Okay. So that is the idea. And what is the electrolyte here? The electrolyte, you have to remember, the electrolyte here is going to be a KOH cell and ZNO. So we are going to have KOH plus ZNO. Any doubts in this?
No, ma'am.
Okay. So as usual, you understand what is happening. So we have this kind of system. So if you look at this cell, the cell will have definitely a like that. Have you ever imagined this cell like that?
No.
Have you ever imagined it like that?
Yeah.
Got the point?
Mhm.
So we have this. So you understand that this is the top is going to be negative and it is a very shiny metal. So below it, so this is basically the anode inside it, but this is the anode cap, something like that. Okay. And then here we have a partition here, just like we had there. And at the bottom, we are going to have my cathode. So the electrons comes outside and enters here like that. Understood my point?
Yeah.
Got it? And in the middle, where do we really have the electrolyte? So here, somewhere near the gasket here. Here. The separator is there. So on the either sides of the separator here, we are going to have Zn, O, and KOH. So we have a lot of OH negative ions in the electrolyte. Understood my point or not?
Yes, ma'am.
Got it?
Yeah.
Now, so how is this basically working? This cap is made up of zinc. Inside it, ZnO is being filled out. Zinc amalgam is filled. So it is pure zinc amalgam is just nothing but just to make a paste of zinc so that it doesn't solidify. We mix it with mercury, mercury being least reactive. So we have ZnHg, and the cap here is made up of zinc. So who is actually losing electrons? It is zinc and zinc amalgam. Anywhere we have zinc. So at anode, what do we do? At anode, what do we do? Just tell me that we are going to have zinc, okay, or zinc amalgam. It becomes and it loses two electrons. Got the point?
Yeah.
So zinc will become what? Zinc will become Zn plus 2. When zinc will become Zn plus 2, it will combine with 2 OH negative from the electrolyte. So it is going to form ZnOH whole twice. Am I right?
Yeah.
And it is going to lose two electrons. So I hope you're understanding that one zinc, just the way we had zinc losing electrons, the cap becomes Zn plus 2 or the amalgam has Zn plus 2, that immediately combines with 2 OH negative. So ZnOH whole twice will eventually become what? It will become ZnO and it will leave lot of water. No issues on that.
Yeah.
You understand? Now these two electrons go and they reach the carbon state. Through the carbon, because carbon is not going to change its state. So through the carbon, they exactly enter where? They enter the cathode. You understand? They enter the cathode. Cathode has carbon along with HGO all along itself. So here in cathode, we have a carbon, mixture of carbon and HGO. Carbon is used to do what? What is carbon going to do? Carbon is going to do the electrolysis of the carbon is going to allow to transfer the electrons, and Hg will be divided into Hg plus 2 and O minus 2. I hope you're understanding. Okay. So the moment these electrons they come from zinc, they enter here. Here we have HgO. So where do you think HgO going to break down? It is going to be Hg plus 2 and O minus 2. I hope you're understanding.
Yes, ma'am.
And when this happens, so this is exactly going to be what? That the electrons lost by zinc in the zinc amalgam at cathode, these two electrons are gained by mercury. So mercury, when it gains two electrons, what does it happen? It becomes pure mercury. O minus 2 is left out. Now understand what is happening. Do you understood that Zn combined with OH negative to form Zn zinc hydroxide? And zinc hydroxide is not very stable, so it immediately breaks and forms water. Water from there converts, passes the separator, and it passes separator and it comes on the either side of HgO.
Mm.
That water will combine with this O. Water is what? H plus and O minus 2. Am I right? Because water is H2O.
Yeah, yeah.
So every O minus 2 and every O minus 2 they will combine and they are going to form two OH negative. I hope you're understanding. So you see, this is regenerating back those two OH negative with zinc utilized. Are you understanding? So here the electrolyte is not getting utilized at a very fast speed. So that is why you understand it gives you a constant potential of 3.5 volts, 1.35 volts. Are you understanding? So otherwise, what would happen every day this would happen that this cell will become weak and every day your wristwatch will stop. But is that happening every day? No.
No.
Why? Because the electrolyte is getting regenerated. Are we understanding my point or not?
Yeah.
Got the point? Very simple part, very simple part, and this is going to be my answer. So you have to understand that what is exactly happening. Just a quick recap. What is cathode? Zinc oxide and zinc and zinc amalgam. And what is this is anode, and what is cathode? It is a mixture of HgO and carbon. Separated by a separator. On the either side of separator, we have what? We have a mixture of HgO and ZnO. Are we understanding?
Yes.
And once that happens, then what happens? That at anode, it is a zinc metal which loses electrons. The moment it forms Zn plus 2, it combines with the two hydroxide ions of the electrolyte. And then ZnOH not being very stable, it will form what? ZnO plus H2O. Are we understanding? And
Mm.
because it forms ZnO and H2O, what exactly does that mean? Just tell me. What exactly does that mean? So it is going to form ZnOH whole twice. So if we have ZnO is a part of electrolyte, you understand.
Yeah.
And from the KOH, we utilize two OH negative, those two OH negative are regenerated here because the moment HgO gains electron, it forms a pure mercury
Mm.
and it forms two electrons, right? So O minus 2 is left, and the water which crossed the separator and came on the cathode side, that water will combine with O minus 2 and it is going to form because water normally, how we study, it breaks into H plus and OH negative.
Yeah.
Understood the point? So here this O minus 2 will combine with this and there'll be two OH negative. which is again regenerated. So my electrolyte is not getting utilized completely. But what is the drawback of this? The drawback of this process is that overall, entire lifetime. So where do you think that this cell will die? This cell will die eventually when the zinc will get utilized. The anode is the one which is providing electrons, and electrons are the source of charge. Are we
Yeah.
understanding?
Yes.
So the moment zinc amalgam gets utilized completely, so you understand that as and when in the zinc amalgam, what is amalgam? Zinc plus neutral mercury. So when
Yeah.
zinc gets completely utilized, we are left with mercury in the anode side also. And on
Yeah.
the cathode side also, HgO is getting converted into pure mercury. So you understand, eventually when this cell die, it has nothing but mercury. So this mercury is very poisonous substance. So that is why we cannot discard these cells as it is, because eventually we are creating a lot of mercury in the atmosphere. You understand? So imagine a situation where everybody using these button cells, and these are actually also called as Rubin Mallory cells. So these cells will eventually accumulate a lot of mercury. So when they are discarded, what is the first step of discarding them? That we remove mercury out of these cells and then we discard the body of the zinc. Okay, that is the method. So their entire lifetime, they will do what? They will give you a constant potential of 1.35 volt.
Yeah.
So if the question comes that, which ions are kind of involved in it. So do we have any electrolytic ion which is involved in the cell? No, there is no electrolyte being utilized because OH was eventually utilized, but it was regenerated and zinc oxide was also regenerated. Are we understanding?
Yes.
Okay. So this cell will eventually give you a constant potential of one. So these are two primary cells that you're supposed to do. One is the button cell and one is the dry cell. Understood? And the equations you have to remember. But if you do not understand the process, you will not be able to remember the equation. Understood the point or not? Then
Yes.
we have the lead storage battery. This is a secondary cell. Okay. How do we have this lead storage battery? Just understand. So we have this kind of situation. This is a battery. This is a lead storage cell. This is a secondary cell. All right. Here the electrolyte, what do we have? The electrolyte here is a 38%. 38% H2SO4 solution.
Mm.
Understood?
Mm.
And the anode here is lead. The anode here is lead. Okay.
Mm.
And cathode here is what? Cathode here is lead oxide with lead. This mixture of lead and lead oxide. Understood the point?
Yeah.
Okay. So what exactly happened? They are both filled in lead and lead. They are both filled in lead grids. Now, what is lead grids? I'll tell you. Okay. So this is the basic situation. Now, how does it work? Understand that we are going to have one cell I'm going to make. There are multiple cells like that. So this outer jacket is both made up of lead only. But if I'm talking about anode, this is anode. So this will have only lead. So this is called as a powdered, you can say powdered lead. And here we are going to have Pb plus PbO2. I hope you're understanding what are we doing. So this outer jacket, it is basically this outer jacket. This is made up of lead jacket. Inside the lead jacket, we have lead and lead oxide at cathode. Okay. And at anode, we are going to have the lead jacket again, the lead container filled with lead, powdered lead. Sometimes we call this powdered lead as spongy lead. So it's like cutting down the metal so finely, just like we have iron filings. Similarly, we have lead filings. Are we understanding this part?
Yeah.
Are we understanding?
Yes, ma'am. Correct.
Got it? So
Yeah.
this is the idea we had. So we had this let storage thing.
Mm.
Now understand what is happening. So we had this secondary cell, 38% H2SO4 solution.
Mm.
We had this anode thing. Now understand what is happening at anode. Now you understand anode is something which is made up of more reactive metal. And this is the case when it is discharging. Discharging means what? So you want to understand that discharging means the battery is providing me consistently with the current.
Yeah.
And you tell me, when your mobile is fully charged, you are doing a lot of work. When you even you press a button, the button will show some illumination. It shows some light in it around it. So what is that? How is that lighting being shown in the button near the button? Because the battery is giving the button some the LED, the some current. So that LED glows up when you even when you're in the dark room and when you're pressing that button, some illumination you see. You understand? But the moment the battery goes to 1% and less than 1%, the phone dies. That means the battery has no more electrons to give it. There could be
Yeah.
multiple reasons. Either the anode has been utilized completely or the electrolyte has been utilized completely. You understand the point? So on a similar note, what do you think is going to happen? That when we are discharging the battery, that means we are trying to take current out of the battery until the battery dies out of charge. You understand?
Yes.
Okay. But once you are charging the battery, then what do? You put a charger and you put it into the socket. So your socket in the wall is actually acting as a electrolyte.
Mm.
It is actually acting like a electrolytic cell. What is electrolytic cell? It provides you with current. So
Right.
the socket will provide you with current and it will recharge the battery in the mobile. So we are studying the same battery. Now, what is this battery? This battery, lead storage battery, we use it in cars, we use it in inverters. If you have heard of ever seen inverter, inverter has a battery connected to it.
Yes.
So you understand that all throughout the day, when there is electricity, the inverter gets charged, the battery gets charged. But when the entire electricity goes off, then we draw current out of the battery. And hence our entire house's fan and lights can light up. Are we understanding? And if you have ever seen what do we do to maintain that battery, we add consistently acidic water in the battery. Have you ever done that?
Yeah, I've added it.
Yeah. So why are we adding? We are adding that H2SO4 solution. So we get it from the market and we get some H2SO4 solution from that. Understood the point?
Yes.
Okay. So this is why that means we are doing what? We are reading about a battery which can be recharged, which is hence a secondary battery. Understood the point?
Yes.
All
Yes.
right. All right. So we'll do the equations in the next class probably. And we were supposed to do the numericals today, but tomorrow we are going to keep a class. Not tomorrow. Whenever is convenient for you.
Okay.